I'm here at Lux Live with Dr. Russell Foster, who is a neuroscientist with an interest in the functions of the eye. I wonder if you can begin by telling me a little bit about your research into circadian rhythms to begin with.
Yeah, well, I mean, we asked a basic curiosity-driven question, which is how does the eye detect the light-dark cycle to set the internal day, the biological clock, to the external world? I mean, a very simple, straightforward question. And the thing that puzzled us is that the light-detecting task of dawn-dusk detection is a brightness detection task. And that's rather different from what the eye is, normally doing, which is to detect an image of the world, which is grabbing light in a fraction of a second, forgetting it's seen it, and then moving on to the next image. And so we started working on mice who had inherited retinal problems. So they'd lost a lot of their classical visual cells. And these mice, although they were visually blind, could still regulate their clocks perfectly normally. And we thought, hang on, this is extraordinary. A mouse can be visually blind, but not clock blind. There may be something really interesting going on there. And we actually proposed back in the early 90s, maybe there's another class of light sensor within the eye. Yeah. You can imagine when we proposed it, the vision community, just appalled, and I was still quite young then, and so, I remember them saying, are you seriously telling us that we've been studying the eye for 150 years and we've missed an entire class of photoreceptor? And of course, being a bit bullish, I said, yeah, I know. Yeah. And anyway, we hadn't done the perfect experiment, and basically it took us about a decade to show it's not the rods and cones, it's something else. And that something else was a group of directly light-sensitive ganglion cells. Now, the ganglion cells are sort of that outer layer of the retina, which forms the optic nerve and sends information into the brain. So about 1 to 2% of those ganglion cells are directly light-sensitive. And, we've sort of went on to show that, of course, that the eye is the organ of space, gives us a sense of our image of the world, but the critical new discovery but it's also this playing a critical role in being essentially the organ of time. Without the eye and that synchronizing signal to the internal day, then our body clocks will drift, and in humans we'll get up later and later and later and later and just drift through time.
Yeah, if you wander around the show and talk to people about it, everybody knows about circadian rhythms.
I think it's a really good example where simple curiosity-driven research has led to something that will have a huge impact not only on our health, but also our well-being and indeed the way we design our living spaces. I think it's really exciting.
Yeah, but this science, how can the lighting industry take your discovery and apply it?
Well, I think what the lighting industry has to do is define what humans are doing in that particular space at a particular time. So if you want to set the clock robustly, then you need bright morning light. Now, most of us, of course, live in homes which are not well lit. We're commuting to work, let's say, on the tube, so that will be poorly lit. We get to work, and it's usually a poorly lit environment as well. What we should perhaps do is have dynamic lighting, whereby first thing in the morning, when you get to work, you actually have bright, blue-enriched light, which would intersect and stimulate those new photoreceptors maximally. Then perhaps later in the day, you can sort of wind it down. These receptors also are not just clock receptors. They're also doing other things as well, not least alertness. Yeah. So as you increase the amount of light, you increase levels of alertness. And so, and it's by this new receptor system. So again, if you want spaces where people need to be particularly alert, then again, you could install blue-enriched lighting for that purpose. So I see a number of different sorts of applications depending upon what individuals are expected to do.
And of course, this research can be used at night as well for improving rest at night, so yes. Going back home.
I think that's the thing. And instrument panels, I think, in vehicles. Yeah. So what would be the most appropriate sort of instrument lighting if you're driving a car at night? And how can we use light to enhance, for example, alertness without interfering with the visual system for driving? I mean, there's lots of potential applications.
This is in hospital wards as well.
I think one particularly important area is very much within the hospital and the intensive care. If you go into intensive care, it's basically very little strong light-dark cycle. It's basically constant light. That doesn't allow the clock to lock onto a signal. the clock will start to drift, physiology will start to fall apart in these individuals who are particularly vulnerable.
Yeah.
So another great application would be very much within the hospital environment.
Yeah. Just to finish up, do you think there's anything more that the lighting industry can do to take advantage of this research?
Yeah, I think it would be good. It's more complicated than blue light good, red light bad, or whatever. I think it is a sort of a dynamic lighting system. We do now know that the rods and cones contribute. They can modulate these photosensitive retinal ganglion cells. So we do need a bit more research. And I don't think we should just rush in and say, right, we're going to put blue lights all over the place. We need to think of what's going to be undertaken in that particular space, and what's the most appropriate lighting for those different tasks. So I think a little bit reflection before just rushing in wholesale.
Okay. Russell Foster, thank you very much.
Thanks very much.